On this lesson, we will talk about telescopic series. So let's get started. Let's consider this infinite series, so the sum of 1 over n times n plus 1. And let's start by writing out the sum of the first 5 terms in this series. So here we have an infinite series, and let's just consider this a sequence. And let's just add up the first 5 terms in this sequence, therefore the 5 terms in the series. So the first term that we would have gotten is whenever we plug in n equals to 1. So we're going to get the following. The second term is whenever we let n equal to 2. So we would have got the following. The third term is whenever we let n equals to 3. And now let's find the fourth one. We'll simplify all this in a second. And we got our fifth term in this sequence. All right, so now that we have all this, let's just simplify it. So now this is equivalent to just 1/2. The second term, so now this is equivalent to just 1/6. The third term, this is equivalent to 1/12. The fourth term, this is equivalent to 1/20. And lastly, the fifth term, this is equivalent to 1/30. So now that we have the value of those terms, what we wanted to do is we wanted to add them because we want to write out the sum of the first 5 terms in this series. So here we have the 5 terms in the sequence, therefore are the 5 terms in the series. So now if we add them up, we're going to get the following. So if I pretty much get the partial sum, well, not the partial sum. Yes, it is a fifth partial sum, which states if I add up the first 5 terms in the series, this is going to be equivalent to 5/6. So if we were to add the first 5 terms in the sequence, we get the fifth partial sum. So that's going to be equivalent to just 5/6. Now, can we show that the series is neither geometric nor arithmetic? Because if it would have been geometric, we could have used the formula that we discussed in our previous lessons. And if it would have been arithmetic, then we could have used the formula to define the fifth partial sum. But now, the way that it's been written down is not so clear if it's neither geometric or arithmetic, but let's just show that it is actually neither one of those two. So let's start our discussion with showing that this is actually not a geometric series. So if it would have been a geometric series, then therefore the terms that we add in should have some kind of a common factor or common multiplier. Which again, we call that the common ratio. So let's find out. Let's get the second term and divide it by the first. And that is going to be equivalent to 2/6, which is equivalent to just 1/3. So it's saying that we have some kind of a ratio of 1/3. Well, let's see if we get the same ratio if we get the third term and divided by the previous one, which is 1/6. Well, if we do this, we're going to get 6/12, which is equivalent to 1/2. So notice that when we try to find the ratio between the second and the first term, that is not equivalent to the same ratio that we got from the third to the second term. So notice that there is no common ratio. So therefore, it is not geometric. Because if it would have been geometric, then the common ratio should be the same among any term and its following one. So we have shown that this is not geometric. Now, let's show that this is actually not arithmetic. So how can we show that this is not an arithmetic series? Well, if we would have gotten one term, and again, we're going to do the same. Let's find the second term. And if I would have subtracted the one that came before that, which is 1/2, in this case, we have minus 1/3. So now we can see that they have a common difference of negative 1/3. Well, if I would have gotten another term, 1/12, and if I would have subtracted the one that came before that, which is 1/6, Notice that I get negative 112. So now notice that we don't share the same difference. So therefore, there is no common difference among them two. So there is no common difference. Therefore, it is not arithmetic. If it would have been geometric, then to find the partial sum, we could have used the formula that we discussed previously. But we know that we cannot use that formula because we just shown that these terms are not coming from a geometric sequence. And since the terms are also not coming from an arithmetic sequence, therefore we could have used the formula that we have discussed on our previous lesson. So what type of a series is this if it's not geometric or arithmetic? Well, let's continue discussing on this and then we're going to see the connection in a second. Before we move forward, notice that here we're still talking about the same series, the sum of 1 over n times n plus 1. Now let's justify that the expression 1 over n times n plus 1, we could have just written it as 1 over n minus 1 over n plus 1. So how can we justify that? Well, to justify, we can just show that we can write one expression as the other. So I'm going to get the expression on the right hand side. And I'm going to manipulate it in such a way that my result will be the left. Well, notice that at least the left hand side has a denominator of n times n plus 1, which they happen to be the denominators of them too. So therefore, to make it fit, I can multiply n over n on the left, and I can multiply n plus 1 and n plus 1 on the right. And by doing that, I have n plus 1 over n times n plus 1 minus n over n times n plus 1, which they have the same denominator. I can just add the numerators. And here notice that the n's will cancel out. So therefore, I have shown that yes, this is the justification. I have shown that the expression 1 over n minus 1 over n plus 1, that's equivalent to just write as 1 over n times n plus 1. And why is it that we wanted to justify this? Because now, if we come back to the original series that we were discussing, 1 over n and n plus 1, if we have already shown that we are able to just rewrite this expression as 1 over n minus 1 over n plus 1, so therefore we are able to rewrite the whole sequence, because now instead of writing it like this, I could have just written it as follows. So we got the sum of 1 . So there's another way that we were able to rewrite this expression or this sum. And now, this is a new way that we could have written. And why is it that this is true? Well, this is because of what we have shown previously. We are able to rewrite this expression as n plus 1. 1 over n minus 1 over n plus 1. So therefore, I can just substitute those expressions. But now let's pause here for a second. And we can start asking ourselves this question, like, what's the purpose of rewriting the series? At first, we saw that if I were to find the terms and I were to add the first 5 terms, notice that I would just get a value. But now what happens if I rewrite this expression as we just did? And now we do the same task. How about we write down the sum of the first 5 terms and let's see what do we notice. Because we have already shown that the series that we are given, it's equivalent to the series. So therefore, I should have gotten the same result. But let's find out. So let's find the first term in our sequence. So that would have been 1 over 1 over 1 over n plus, oops, not n, but just 1. And I'm going to use some colors here. So let's find the second term. The second term would be 1 over 2 minus 1 over 2 plus 1. Get the third term. That will be 1, 3 over 1 over 3 plus 1. Let's get another color here. The fourth term, 1 over 4 minus 1 over 4 plus 1. And lastly, let's do it on green. Let's get the fifth term. 1 over fifth minus 1 over fifth plus 1. So now, what would have happened if I would have add the first 5 terms? Well, let's see. If I get the first term, so let's get the partial sum of the fifth terms. This is a whole term. So let me just rewrite as it is. So 1 over 1 minus 1 over, so that's a 2. Now let's get the second term. Let's add the second term. 1 over 2 minus 1 over 3. 2 plus 1 is 3. Now if we would have add the third term, we would have got plus 1 over 3 minus 1 over 4. Let's add the fourth term. So that would be 1/4 minus 1 over 5th. 4 plus 1 is 5. And let's get the fifth term. That's 1 over 5 minus 1 over 6. And at least we can stop here because we only want the first 5 terms. But what do you notice about the sum of this sequence or the series that comes from this sequence right here? We notice that now, if we were to rewrite our sum this way, notice that there's something going on with all those terms. Now, negative 1/2 is going to cancel out with positive 1/2. Negative 1/3 is going to cancel out with positive 1/3. Negative 1/4 is going to cancel with positive 1/4. They're going to cancel out. And if we were to continue to add all the terms in this sequence, this term is going to cancel out with the next one. And the next two are going to cancel out. And the next two are going to cancel out. And the next two are going to cancel out. But right now we just want to concentrate on the fifth. But I want for you to notice this pattern. So therefore, this just boils down to the fifth partial sum as of 5. This is just equivalent to the first term, which is just 1. Because all the other terms that are remaining in the sum are going to cancel out. And this is what we refer to as a telescopic series. A telescopic series is a series in such a way that terms in that series are going to cancel out. It's not that always the first term is going to survive. In this example, that's how I set it up. But the idea of a telescopic series is whenever you have a series where terms are going to cancel out, and then you can define the sum as a finite number. And the correct way of saying it is that a telescopic series is a series whose partial sums eventually only have a finite number of terms after the cancellation. Which in this example, notice that this finite number is just one term. So this is just a small example of a telescopic series. But now that we know that this is a telescopic series, let's compute the finite sums. The infinite sums, I should say. Let's compute the infinite sums of this telescopic series. Now, let's give a hint. Let's look at the pattern in number 5, which is what we just did, and think about how this can be used in infinite sums. Well, we just shown that if I'm gonna, well, let me change the color here. We just shown that if I were to add the first 5, yeah, I think we have already discussed this result a couple seconds back. So if I would have added the first term, I would have got 1 over 1 minus 1/2. And if I would have added the second term, it's 1/2 minus 1/3. And if I would have added the third term, 1/3 minus 1/4. And if I would have added the fourth term, that's 1/4 minus 1/5. And if I would have added the sixth term, 1/5 minus 1/6. And if we would have computed all this, then the sixth term, it would have been something along the lines of 1/6 minus 1, 7. And if I would have added the seventh term, it would have been of 1, 7 minus 1, 8. And it's going to continue infinitely. So now, is it possible for me to give a finite number to the summation of infinite terms in this series? Well, yeah, because like we have discussed previously, in a telescopic series, terms are going to cancel out, and you're going to have a finite number of terms, which in this case, they're going to cancel out in pairs. So 1/2, there's 2 cancel out, 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 this 2 cancel out, and now this is going to cancel out with the next one, and so forward. But if we concentrate on the last 2 terms that are going to be present in this series, so we're going to have all those in a bunch of cancellation, and then the last terms, let me make some space here, and the last terms are going to have an expression of 1 over n minus 1 over n plus 1. And if everything cancels out, then I know that this term is going to cancel out with the previous one, and the last term is going to be remaining. So we're saying here that we have 2 terms. We have the infinite sum of n plus 1 is 1 over n minus 1 over n plus 1 equals 1 over 1 plus 1 over n plus 1. But didn't we just say that it's just equivalent to just 1? So what's going on with this term? Well, let's think about what this term is going to be. If we know that we're going to go towards infinity, therefore this value of n is going to be huge. So therefore 1 over a huge number is going to be approximately 0. So therefore we can assume that this value is going to be so insignificant that we can just call it 0. So therefore we can just say that the sum is equivalent to just 1. It's like if we were to say, well, round out the following number. Well, instead of writing all those ones, I mean, this is definitely not equivalent to 1, but it's definitely super close to 1. It's 1.00000 all 1. But we can just say at the end, well, 1 plus a small number, that's just very equivalent to just saying 1. And let's just summarize what we have done here. So what we have done is first we have shown that the initial series can be written in a different way. That's supposed to be an n. This is what we have shown. We have shown that this infinite series was able to be written in a different way. But now, let's think about how was this useful to finding the infinite sum. How is this technique useful to finding the infinite sum of the original series that we were given? Well, if we were to try to find all the terms. So initially, we stated that this initial series, it's neither geometric nor arithmetic. Therefore, we cannot use the sum formulas that we have discussed previously. But we saw that there was a different way that we were able to rewrite the function. We were able to just look at the expression and write it in 2 different terms. And we noticed that if we were able to rewrite in different terms, if we were to try to find the sum of my new expression, we notice a pattern of cancellations. So if the majority of the terms are going to cancel out, if not all of them, then it's definitely easier for us to identify the sum, which pretty much is just going to be the number or the term that is going to survive there. And we have shown this, that even in an infinite series, we can say that this goes approximately to 0. Even in an infinite series, like, we can still use the same idea to come up with the proper result. So therefore, it is very useful because we were able to. So what we have done, we were able to find a finite value of an infinite series. We were able to find a finite value of an infinite series. And I welcome you to take a look at the initial series and just write out the first 30 terms if you want to, or 20 terms, and add them up. And you will see that there will be no values that are going to cancel out. But if you write the first 100 terms, even 1,000 terms, and you decide to add them up, those values are going to get closer and closer to 1. But it's easier to see it this way because we can see a pattern of cancellation. So that is what a telescopic series is. It's a series where all the terms are, not all, it's a series where the majority of the terms are going to cancel out, and you're going to have a finite number of terms that survive the cancellation process, and you can just add up those terms and come up with a finite value. Well, let's take a look at one example to see how this is useful. So let's take a look at example number, let's call it example number 1 now. Let's go look at example number 1, and let's compute the finite sum. Let's compute the finite sum here. Well, notice, so if we have an expression that perhaps denominator, it's composed of multiplication of two factors, which in this case you have n plus 1 and n plus 2. This might be a good candidate for us to try to rewrite it to see if the sequence can fit the definition of the telescopic series. So therefore, our first job is going to try to write out the given expression, 1 over n plus 1, we want to see if we can rewrite this expression in such a way where I have one denominator in one term and another denominator in another term. One factor in one term, should I say, and the second factor in the second term. But notice that we have done examples like this. And what we're going to be doing here is try to find out the correct coefficients or the correct numerators in such a way that if I add them up, it gets me the original back. And remember that this is a technique that we discussed a while back, which is called partial fraction decomposition. So we're going to be using partial fraction decomposition to properly rewrite the original series. So let's do that. What we have shown is I have this expression, and I want to rewrite it in such a way where I need to find the correct values of those numerators so that both expressions are equivalent to each other. So this is our setup for partial fraction decomposition. So if you recall the process for partial fraction decomposition, the first thing that I want to do is multiply the denominator of the given. So I'm going to multiply n plus 1 times n plus 2 on both sides. Oops. This whole thing is going to multiply by n plus 1 times n plus 2. That way, by doing this, notice what we have. Now, this is going to cancel out, so now I have 1 over, but if I get this expression, and if I get distributed to the first term, notice that n plus 1 is going to cancel with n plus 1, so I only have a times n plus 2 plus. And if I were to distribute to the second term right here, The n plus 2's are going to cancel out. So the only thing that's going to be multiplied is just n plus 1. And let's just distribute this a little bit more. Let's just distribute this a little bit more. So we got an plus 2a, if I distribute the a's, plus bn plus 1. And if you remember, what you want to do is you want to group those that have the variable, which in this case the variable is n. So we can rewrite this as n times a plus b plus 2a plus 1. And now that we have done this, we want to match up the coefficients. So, but notice that the value of 1, this is also equivalent to 0n plus 1. And why is it that I want to write as 0n? Because here we have a value, a variable of n on left and the right. And now we want to just match up because I want to make sure that they are equivalent to each other. So the coefficient of n on the right-hand side should be equivalent to the coefficient of n on the left-hand side. So therefore, a plus b should be equivalent to 0. In addition of that, the constant on the left, which is 1, should be equivalent to the constant of the right-hand side. So therefore, we have another equation. We have the equation that 2a plus 1, this is equivalent to 1. Sorry, I just noticed that this is not a 1. This is supposed to be b because the b gets distributed, so this becomes a b. And if we carry this out, this is not a 1, so this is a b, and therefore we have it right here. And I notice I have a system of equations where we have two variables and two equations. So let's just modify this. From here, we can say that a is equivalent to minus b. So if we were to subtract the minus b to both sides, we got one solution here. So now that I know that a is equivalent to minus b, I can plug in this result to the second equation. And we'll do that over here. We're going to get 2 times minus b plus b is equals to 1. All I did, I substituted the value of a with minus b, and now notice I have one equation with one variable. So now this becomes minus 2b plus b equals 1. So now this becomes, what's this? Minus b is 1, so therefore b is equivalent to minus 1. And since b is equivalent to minus 1, so therefore a is equivalent to minus b, but we already know that b is minus 1, so therefore a is equivalent to just 1. So now that we properly know the numerators for the partial fraction decomposition, now we can say the following. Now we can say that the infinite series that we were given we said that it was equivalent to a over, so since they're equivalent, so they should have the same sum. It should be equivalent to a over n plus 1 plus b over n plus 2. But we already know what a stands for. A stands for 1. Therefore, we can substitute this for 1. And b is minus 1. So we have minus 1. But notice that this just doesn't look right. So instead of writing plus minus 1, I'm just going to write this as just minus here and positive there. So notice we're able to rewrite this infinite series in a way that kind of looks like the example that we have done previously. So this might look like a telescopic series. Well, let's see. If we want to compute the infinite sum, so all we got to do at this point is just actually start computing terms and adding them up. So we got n minus 1 plus 1 minus 1 over n plus 2. Let's start finding those terms. Let's find out the first term. Well, the first term is going to be 1 over, let n equals 1. So we got 1 plus 1 minus 1 over 1 plus 2. So this is the first term. Let's find the second term. Well, let's plug in n for 2. So we're going to get 1 over 2 plus 1 minus 1 over 2 plus 2. This is the second term. Let's go all the way to 5. So to get the fifth term, let's plug in n equals 5. This is the third. Oh, I'm sorry. So this is the third. That this should be 3 is not 5. Sorry. Let's compute the fourth term. So we're going to get 1 over 4 plus 1, 1 over 4 plus 2. And let's actually stop at the fourth term. We're not going to go all the way to fifth. So the fifth term, you can compute it yourself. But now, let's simplify all this. So if we were to simplify this, and again, we're not going to talk about this example. So let's just block it here on the side. If we were to find the first term, well, that's equivalent to 1/2 minus 1/3. This is the first term. Now let's find the second term. Well, that's 1/3 minus 1/4. Let's get the third term. So that's 1/4 minus 1/5 plus 1/5 minus 1/6. And it would just keep continuing adding up. But notice that we already have the pattern that we were looking for, because now 1/3 is going to cancel out with this 1/3. 1/4 is going to cancel out with this 1/4. 1/5 with this 1/6. Fifth, 1/6 with the following, and so forward. So therefore, now we can say that the infinite sum that we were given of 1 over n plus 1 over n plus 2, we said that this was equivalent to the infinite sum that we were just computing. And we have already shown that this series is equivalent to just 1/2. So therefore, our conclusion is that the infinite sum is just equivalent to 1/2. So this has been a small lesson regarding telescopic series.